Okay, good afternoon, everybody. Thanks for attending this presentation. It was supposed to be a double act today. My colleague could not make it, so it's going to be just myself. So just a quick word of introduction. So I'm Jean-Philippe Villain-Chastre. I'm not going to tell you where I'm from. I will let you guess from my accent. But I'm based at Messier-Bugatti-Dowty, looking after the R&T department. So I'm an R&T project manager. And today I'm going to give you an history of Messier-Bugatti-Dowty, so who we are. I'm going to give you as well a little bit more information about what we are doing in terms of research and technology, so it will be a very top level presentation. And since we are talking about manufacturing today, I will give you more information about success story that we've got at Gloucester and across the other sites. So first of all, a quick word of introduction about Messier-Bugatti-Dowty. So we are part of the Safran Group. So Safran Group is a big French aerospace-based group looking after aerospace, defense, and security. It's an international high-tech group, I should say, employing more than 70,000 people across 55 countries in the world. And if we speak about turnover, the turnover of last year was over 17 billion euros. So you can see the size of it. As I said, 3 core businesses, aerospace being the biggest one, and then we've got defense and security. If we look a little bit more in details around the Safran Group, on those slides, a little bit busy, but you can see the spread and the distribution of the different business units for Safran. So half of Safran is for the propulsion for aircraft, but also rockets. That mainly through the company called Snecma. Snecma is probably well known for the CFM56 engine. It's the best selling engine for aircraft in the world. And Turbomeca. I am part of Messier-Bugatti-Dowty, so we are considered as part of the equipment division. We are half of the equipment division of Safran. And then you've got the 2 other divisions, a little bit smaller, defense and security, but they are growing market as well. In terms of Safran in the UK, so as I said, it's a truly global organization. Half of the business is performed in France, but the other half obviously is worldwide. UK being one of the biggest countries employing and generating turnover for Safran. So we've got 7 different sites in Safran in the UK. We have 2 sites in UK. I'm based in UK. So we've got 1 site for the landing gear division and 1 site for the services of those landing gear. So if you want to glorify it, it's like a garage for your landing gear. Every 10 or 14 years it gets repairs. But we've got other sites as well spread across the UK. If you go a little bit more in the north, you will have Aircel in Burnley. So Aircel are doing the nacelle for the casing for the engine. Going down a little bit more on the east side, you find Labinal Power System. They are doing all the electric wiring for aircraft. Going down south, you will find Morpho in London. Morpho are doing all the security equipment. If you go to the airport and you go through one of those scanners, it's probably going to be one of the Morpho scanners. So it's all security and detection. And then we've got Turbomeca UK. So that's purely a repair facility. So they repair the engine for helicopter. They are based in the south of England. And finally, we've got Safran Engineering Services based in Bristol, looking after providing engineering services for the Safran company, but also outside of the Safran Group. So in terms of turnover for Safran, the UK is around 7%. So that's £1 billion, which is quite significant number, and it's a growing number. And it's around 3,000 people employed all around the UK. Now I'm going to give you a little bit more about Messier-Bugatti-Dowty because this is where I am from. So Messier-Bugatti-Dowty is a result of a merger of 3 different companies that took place in May 2012. So it was Messier-Dowty on one side, the world leader in the landing gear design, production, and services. Messier-Bugatti, they were the world leader in terms of design and manufacturing for wheels and brakes for aircraft, but also other industry, such as Formula One, for example. And finally, Messier Services. So Messier Services is what we call an MRO, maintenance, repair, and overhaul. And as I explained, it's where all the landing gear at some point in their life will be repaired because we have some corrosion, because we need to check the integrity of the landing gear. So back in 2012, with Fusion, we merged those three divisions, and we created Messier-Bugatti-Dowty, who is now the #1 in terms of design, production, assembly, and services of landing system. In terms of numbers, globally we have a turnover of around 2 billion euros. I will show you a slide. The next slide will show you the different sites across the world, and you will see it's quite busy. And we employ more than 7,000 people. So it's around 15% of the Safran group. So in terms of industrial footprint, I'm not talking about headquarters or design office here. I'm only talking about industrial footprint because this is why we are here for today. As you can see, it's quite a busy map. We are basically everywhere around the world. The biggest historical sites are based in Europe. So we've got one big site in Gloucester where I'm based, and one big site in the southwest of France, not far from Pau, not very far from Toulouse. So that's the two historical sites for Messier-Bugatti-Dowty. But also we span across different countries, so we have big sites in China. We followed Airbus, our main customer, to China, and we are also looking after a low-cost implementation. We are in North America. We've got two sites in Canada, one in Montreal and one in Toronto, producing large components, but also serving the North American market in terms of business jet and military aircraft. And finally, we have one site in Mexico that's more looking after the dollar zone and the low cost as well. All the other sites in purple on the graph are located in US or in France, and I'm mainly looking at producing carbons for the carbon brakes. Few numbers with regard to Messier-Bugatti-Dowty, so that's quite impressive numbers. I know that in terms of aerospace, we always talk about low volume, but when you start to look at this, it starts to be quite interesting for us. Today we equipped more than 25,000 aircraft with either Messier-Bugatti-Dowty landing gear, system equipment, or wheels and brakes. So it's a large fleet of an aircraft. If you take any plane today, whether it's a small business jet or a large commercial aircraft, you are likely going to fly with our landing gear. We have over 30 airframer customers. So we all know the two big ones, Boeing and Airbus, but there is 28 on the side that we serve as well. That's over 900 airlines. And a number that is quite significant. We've got one aircraft taking off or landing with our landing gear every 2 seconds. So it's when you start to see that it's quite a moving industry. In terms of large aircraft, this is 65% of our markets. And then, as you can see, we also equipped regional aircraft, business jets, and also some helicopters. Just a quick focus on the Gloucester site before we start to move into the presentation. So the Gloucester site is one of the biggest sites for Messier-Bugatti-Dowty, and it's probably the only site where on the same area we design the landing gear, we produce the landing gear, we apply some special processes on the landing gear, we assemble the landing gear, and we also can test the landing gear, and finally we can repair the landing gear. So it's a completely integrated site. The site itself was created in 1937, so you can see it's an historical site. It spans over more than 100,000 square meters, so very large site spread across the main road. We employ roughly around 1,000 employees, and as I was saying, it's a real driver in terms of sites for the whole cycle life, from design of a landing gear all the way to services of a landing gear. And of course, we are striving on the recruitment of apprentice graduates. I'm a graduate myself back in 2008, so we are really trying to get young people into engineering for the landing gear. And as I said, that's 40,000 takeoff and luckily 40,000 landing as well on a daily basis. So that's for a bit of corporate presentation. So now I'm going to go more into the presentation itself and giving you some information about what we do in terms of research and technology and why it's very important for us to focus on being innovative so that we can stay number one. So first of all, that's a quick slide explaining you the evolution of the landing gear, I will say, over the last 20 to 30 years. So we had massive change, basically, 30 years ago. If you look at a landing gear which is the size of an A330 aircraft, most of the landing gear was designed using low alloy steel. So it's steel with a UTS of above 1900 MPa for those who knows. Single brace attachments. There was not much composite 30 years ago on the aircraft, so we only had one single point attachment of the landing gear. The braking system was completely hydraulics. 30 years ago, we did not speak that much about being REACH compliance, so the whole landing gear was cadmium plated and chromium plated. And in terms of pressure, we were designing the landing gear based around 3000 psi for the hydraulic pressure. With the introduction of the latest state-of-the-art twin-aisle aircraft like the Boeing 787 and the Airbus A350, we produced the main landing gear for those two programs. We introduced a lot of new technology. Titanium, which was extremely small proportion 30 years ago, is becoming the major material used on those landing gear. If you go on the stand, which is next door, you will have two mock-ups of the two main landing gear for A350 and 787, and you will see that most of the core parts are produced in titanium today. Why do we introduce so much titanium? It's purely because we need to have a product as light as possible. You have to remember that apart from the taxiing, the takeoff and the landing, the rest of the time we are literally a dead weight in the aircraft. And when you look at the weight of the whole program, maybe 3 to 4 tons, it's quite a very heavy dead weight to carry from one continent to another. So we really need to reduce the weight, which is why we introduced more and more titanium. Because the composites today are made of, the aircraft are made of more and more composites, we had to go from one single brace attachment point to a dual brace attachment point, which is some tricky problem for us because it means that we are now in a hyperstatic system rather than being an isostatic system. Looking at the braking system, we were the first brake manufacturer to introduce electric braking system for the Boeing 787. So we start to move from a hydraulic braking system to a more electric system. We started to introduce REACH compliance coating. So the chromium has been replaced by high velocity oxygen fluid, HVOF, based on tungsten carbide cobalt chrome. And finally, the pressure used in those aircraft is increasing. We are now talking about 5000 psi, which presents some big challenge when you design a landing gear. So the question mark here is what's coming up in the next 20 years. We saw already a big gap during the last 20 years, so we need to prepare the future. We need to be ready to the next requirement from our main customers. We are working on this. In fact, we were awarded by Innovate UK a large funding very recently in Gloucester to start working on the landing gear of the future. And we'll be looking at something which is lighter, which is cheaper, obviously, which is environmentally friendly, which is sustainable, and that will fit with the demand of the customer. So the driver for the development, just a quick reminder that we are positioned in a very lucky industry, if we can say like this. Looking at the growth in terms of aerospace since the 1970s, you can see that we did not suffer from any major recession. We did not suffer from any political crisis or oil price crisis. And every time aerospace, because we have such a large order book in front of us, we always manage to prevent any dips, which is quite a secure thing to be in. If you look at the increase on the landing gear since the 2000 years, so over the last 15 years, we've nearly doubled the demand for aircraft. And the numbers coming up from Airbus and Boeing is that the global fleet is going to double between today and 2030. So we have a step ahead of us, which is even bigger than what we've seen so far. So we are lucky enough to have an industry driving us. But we need to work on competitivity. We need to be innovative, otherwise our biggest competitors will start to get some of the markets and we won't be in a position of world leader anymore. So there are some areas that we are looking at. We are obviously listening a lot to our customer because they are driving the demand for landing gear. So you have on one side the customer requirement, which is what I'm presenting now. As I was explaining, we need to have a landing gear which is as light as possible. You don't want to carry 3 tons of landing gear of metals from Europe to America twice a day. You know, it's a lot of fuel burn that you could prevent, or it means that you could add extra passenger in your aircraft. So the low weight is a key driver for us. Low cost of ownership, that's direct impact to the airliner, not the airframer. The airliner need to have their aircraft flying. Whenever the aircraft is parked on the runway, they are losing money. And you can understand that if we have issues with the landing gear because of corrosion, because of some maintenance we need to do with regard to the greasing and so on, the airliner will not like this. So we are looking really at a landing gear. If we could call it like this, that will be a kind of fit and forget. So you put it on the aircraft, you forget about it, and you just can run your aircraft as you will run a normal car. The reliability and durability. I was talking about the garage, the glorified garage for landing gear, your overall shops. Today, the biggest time we've got between 2 overall is 14 years. Is to say that every 14 years, the landing gear will have to be stripped completely. We will have to remove all your painting, all your coatings. We will have to remove the corrosion, because corrosion is the #1 issue on a landing gear. We still have some steel component, and steel components, despite being protected with coatings, will rust at some point. You know, we operate in a very harsh environment, so any debris that you can find on the runway can impact the landing gear and can remove some of the coating. So once the base material is exposed to the environment, you will rust. So you need to repair this every 14 years. When you speak to the airliner, 14 years is way too short. They want to have something of 20 years. So they want not to have to touch the landing gear for 20 years. And today it's a big ask for us, and we can't do it right now, which is why we are looking at how to achieve this 20 years overall period. Finally, sustainability, that's more the impact that our product can have on the environment, but also its societal impacts. When you live near an airport, you don't want to hear the noise of the aircraft all the time. And you have to know that 50% of the noise generated by an aircraft during landing come from the engine, from the landing gear. It's not the engine, because the engine is on idle. So 50% of the noise is landing gear, which is why we really work also towards reducing this noise generated, because it's badly perceived for anybody living around an airport. So that's really what the customer, the direct customer wants. Now we are also part of working industrial group. That's your ACARI project, for example. So ACARI stands for Advisory Council for Aviation Research and Innovation in Europe. So that's really looking at what is the requirement for the aerospace from an industrial point of view, but also from a human point of view. How can we make the aerospace industry as an overall greener, more acceptable, and how can we have a positive impact on the environment rather than negative impact? I've put here some key bullet points that were quite important. If you look at the targets that we have for the Flight Path 2050, it's quite aggressive, and we are quite far from being there yet. When you speak about 75% reduction in CO2 emission per passenger, we have still quite a long way to go there. Obviously, the weight of the landing gear is a direct contributor. The heavier you are, the more fuel you are going to consume, so the more you are going to pollute. But we also have some target of noise emission reduction, as I was saying. And in this program, it's 65%. So we need to find a way today to be twice more quieter than we are at the moment, which is not always easy. So that's really for the key external driver that we need to take into consideration when we perform research and technology on the landing gear to develop a better product. Now I'm going to talk to you about 3 or 4 very top level technology. I'm not going to go in details today, otherwise we could spend the whole afternoon, and I don't think you'll be staying here. So that's really a top level overview. If you have some question, I can reply later on. So the first one is health monitoring. So it can seem quite simple. Everybody driving a car today will have some sort of health monitoring on the car. All the engine manufacturers for aircraft use health monitoring today. In fact, the engine on each aircraft is sending information during the takeoff, during the flight, and once it's landed, permanently pinging information about the temperature, the speed of the rotation of the shaft, and a lot of those information. So it's a mature technology for a lot of application. Unfortunately, it's not there yet for a landing gear. A landing gear, it's much more complex because we are handling some loads that are completely different from what an engine can see. You have to remember that if we speak about an A350 type of aircraft, you speak about not miles away from 300 tons that you have to land in different conditions, in different weather, with different wind, different type of runway. So every single landing, I will say, is going to generate a different load path on your landing gear. And being able to find the best sensor, the best system out there to monitor what's happening in terms of material is extremely difficult. So we're working on it. We're trying to look at existing solutions and implement them on a landing gear, but we're also working on developing our own sensoring device so that we get in permanent have information about the landing gear. Obviously, it's a massive gain for us if we manage to do this. First of all, in terms of maintenance interval, I was telling you earlier that an aircraft landing gear will be repaired every 10, 12, or 14 years. It depends on your program. Well, if you have a way to find the behavior of your landing gear and the health of your landing gear, you may be able to extend this overall period to 16 years without doing anything. So that's a critical point for us. Another key area is to predict the life remaining in the landing gear. Today, if an aircraft lands very hard, so we call this a hard landing, it's extremely difficult for us to understand how badly the landing gear has been damaged, what part can be reused, and what part will have to be salvaged because they are not safe to flight anymore. With health monitoring, basically, you will understand the load that went through your component, and it will be very easy for you to kind of predict how many cycles you can apply on this component in the future. And finally, it will highlight, obviously, any issue, any risks that we have with the landing gear, and it will help us to develop better products for the landing gear. So for us, it's a very, very interesting business that we are pushing forward. It's also a change of business potentially for us, trying to apply something like a landing fees rather than selling a landing gear. So it's something that is quite critical from our strategy. I've put two examples of sensor on the slide. That is sensor that we have developed and that you can buy off the shelf anywhere, that you can adapt to the landing gear. One of them is your shock absorber pressure monitoring system, so to try to understand what is the pressure in your oil and in your nitrogen. And the second one is the wear on the tire. So we don't produce tire, but we are very interested in knowing what is the wear and the life left in your tires because it has a direct impact on the landing gear. So that's for our health monitoring. Electrical actuation. I'm sure that everybody heard it's a buzzing name, a more electric aircraft. Everybody is working towards it. Everybody wants to plan for 2030 or 2050 a fully electrical aircraft. So we need to follow this. We can't be the only system on an aircraft using hydraulic fluid for different reasons, but we need to really look into electric actuation. So we are looking at two different types of electric actuation system. One is EHA, electro-hydraulic actuation, and the other is EMA, electromagnetic actuation. The two different systems offering pros and cons. So rather than betting on one technology, we are developing the two in parallel. And ultimately, for us, if we can have a full electric landing gear, it means that you can get rid of all your hydraulic system. So that will contribute to a lighter landing gear because electric is lighter. That will allow us potentially to enhance the performance of the electrical actuator. And most importantly, we will contribute to reducing the negative impact on the landing gear on the environment. Electric, you have no risk of fluid leakage and so on, so it's a greener technology. Finally, when we speak about electrical actuator, we need to think about redesign of an actuator. So it's a good opportunity for us to start to combine different functions within an actuator to try to reduce and simplify the way the actuators are designed today. The last top-level technology I'm going to talk about before going into manufacturing is a maintenance and corrosion-free landing gear. So as I was telling you, the dream of any airliner will have to have a fit and forget landing gear. So you install the landing gear and you don't have to care about it anymore. One of the possibilities to have this is to go through the development and the adoption of high-strength stainless steel. If you go outside the seminar theater, just on the MBD stand, you will see the largest high-strength stainless steel landing gear. It's the largest in the world. That's an ongoing project with our main customer, Airbus, that we started around 4 years ago. And the aim really is to replace the low alloy steel that are extremely corrodable with high-strength stainless steel that will not corrode in the future. Obviously, if we have a base material that is not going to corrode, then we will care less about the debris on the runway that will impact the landing gear and that will remove some of the protecting coating. So the base material is extremely important, and we believe that stainless steel is one of the biggest hope for our industry. So that's for the top level presentation, and again we are working on a lot of other area, the design of a landing gear, the assembly of a landing gear, the different coating we apply on landing gear, but what I wanted to do now is to give more information about what we do in terms of R&D for the production. So we are investing a lot of money to make our production more efficient. If we look at a site like Gloucester, we are a saffron center of excellence for machining titanium, and we need to develop more and more production technology to be efficient on titanium. The move from steel to titanium around 10 years ago was quite traumatic for us because titanium is much harder to machine than the steel. So we are developing a lot of continuous efforts to be as efficient as we can on this technology. So this is just showing you the R&D advanced manufacturing segment, looking at the improvement of production. 70% of the technology we are developing have to be employed or deployed in the shop floor within 18 months. If you need 5 years to develop a production technology, then I think it's too long in my view. You've missed the boat. So in order to support the ramp up, you need to develop something rapidly. But obviously we speak a little bit as well about future technology as well, and I will speak especially about additive manufacturing later on. So as you can see on the screen, we look at the titanium machining as one. So that means new cutting tool, new machining strategy, new way to cool down the tooling during machining, swarf evacuation. So that's really to be more efficient in terms of pure manufacturing. We look as well at optimizing the current processes, because sometimes it's easier to optimize your processes rather than trying to change everything. You can have a lot of quick win like this. So we try to be better at industrializing our product. We try to be better at understanding the heat treatment, for example, because heat treatment can cause a lot of distortion, and any distortion you will have during heat treatment is non-added value that you put in your product. So we need to be efficient in this area. Obviously, automation is quite a key area for us. We believe that for repetitive tasks and for area where you can have a health and safety hazard to the human, then automation will have its place. If you compare automotive to aerospace, it's two completely different industries. We are not going to put a robot when we need a cycle time of 60 hours. It doesn't make sense. So we try to identify really the niche area in the industry where we can implement this. And I was saying, we are also preparing the future, especially with the introduction of additive manufacturing. So that was to show you the top level story. Now I've got a few slides explaining a little bit more in details example of success story. So it's projects that we've done at Messier-Bugatti-Dowty and that are implemented at the moment on the shop floor or will be implemented this year. This first project, it's a very simple project. It was in partnership with the AMRC. Messier-Bugatti-Dowty is tier 1 member of the AMRC, and we work a lot with the High Value Manufacturing Catapult Center in UK. So the objective on this project was to reduce the finishing machining time of one specific component in high strength titanium, and we wanted to be quite aggressive. We really wanted to make a massive impact. So it was a 2 stages project. The first stage is with the AMRC doing a lot of machining trials on very simple bars, trying up to 10 different new cutting tools from supplier. And the second stage was to conduct some machining trials on a production part at Gloucester. So the second stage is always a little bit tricky because you are playing with a part which is worth more than a very, very nice car. So you can't mess up with this. You can't take the risk of creating a scrap, otherwise that's a bit of trouble. So we always try to keep this 2 phases approach. And ultimately on this 9 months project, we managed to change our machining strategy. So we went from pure plunge milling to zigzag milling, which allowed us to remove the cutting time in the air from 50% to only 10%. So 90% of the cut is in contact with the part. So we optimize this. But we also introduce new type of ball nose tools, as you can see on the screen, trying to introduce more fluids on this component so that we can be more efficient. Combining those 2 technologies, so a new strategy with a new tooling, allowed us to save massively in terms of lead time reduction, but also we saved a lot of money on the consumable, so on the cost of tooling, which is a direct cash for us. So it's quite important for us. Obviously, as I'm saying here, when we do this kind of project, we always have a team with different people involved in it. The inspection is very important because when you change your machining strategy or your machining tools, the surface of the part of your component is going to be different from what you used to have. And the first thing your inspector is going to tell you when you look at the new part is, I'm going to reject this because it's not compliant. So it's always important to have this full life cycle. Another project which is ongoing at the moment, that's in collaboration with the Manufacturing Technology Center, the MTC in Coventry, is looking at trying to automatize the inspection of landing gear. So we are talking about landing gear for a single market. Today we spent around 1 day to look at each of those landing gear. We've got more than 400 points, so we've got a checklist with 400 points to check on this landing gear to make sure that we have the right part number, that we have no leakage, that we have no scratches on the paints, that the sealant is where it should be. So it's quite a long lead time. Moreover, when you look at the increase in volume over the next 3 years, we are going to double the production of this type of landing gear. So we can't just continue to do what we do today. We are not efficient. So the idea of this project is quite simple. We want to take a robot, a simple robot that we will equip with an optical means. And the idea is to take picture of the landing gear in different area and to use off-the-shelf algorithm to inspect the picture that we have just taken and to try to detect if we have the right part number in the right place, if we have some damage on the part that we have not seen, if we have the sealing in the right area. So it's really trying to be as efficient as we can on the inspection. That's a project that started around 6 months ago, and we are targeting an implementation on the shop floor the first quarter 2017. So next year, but we are already doing a lot of progress by doing single inspection on a single points component at the moment. So that's the kind of project that we'll be looking at reducing the lead time for inspection. We speak about inspection again on this slide. That's a very, very detailed inspection. As you probably imagine, when we machine completely a component for a landing gear, we have to put a lot of time in inspecting this component. So we inspect mainly the surface of the component to make sure we are not going to have any area where stress could be localized and that could create a defect in the landing gear in service. So we need to make sure that the surface is compliant with our spec. And in this project, we've developed a specific algorithm. So again, we are taking a robot on which we are mounting a very detailed 3D microscope. In this case, it's an Alicona for those who know. And we are developing some algorithm to try to calculate your waviness, your radius, your mismatches, and try to see if this is compliant with our spec or if it's out of spec. If we don't do this, we'll have to inspect manually a complete landing gear with rugomizator, taking prints of the landing gear and looking under the microscope, and that is taking hours. So this solution will allow us to be much more efficient. Very complex project because developing algorithm to calculate the mismatch of machining is very, very tricky. We spent the whole of 2015 working on those line of calcul, but today we are in a position where we are going to implement this project in the south of France first, but across all the other sites sometime at the end of 2016. Another project which is a kind of quick win project which is quite interested. So that's to paint the axle of landing gear. So as you can imagine, and if you go on the stand next door, you will see a landing gear with two big axles. The axles currently are produced in low alloy steel, so they will corrode. So we need to have a very robust protection plan for those parts, which means that we need to paint inside this axle with two different types of paints, a primer and a top coat, like you will have in any industry. The biggest axle we have on site is around 2.2 meters. And we were asking the operator to paint with a 3-meter lens and to apply a coating of paint within 10 micrometer. 10 micrometer, it's a fifth of an average human hair. So imagine trying to paint something where you have no access, no visibility within a very tight tolerance. It's clearly impossible. So in this case, with the MTC, again in Coventry, we've developed a completely automated system that is managing the paint mixing, the paint distribution, and the paint application, fully automated. And we installed the system back in September. We are still commissioning the system because we are learning with the technology, but we managed to reduce the tolerance that we have within 5 microns. So we have a 100% repeatable process from one axle to another, which is extremely key for us. It's a quality. So we don't have to rework the part anymore. We've got a part right the first time. And because of the product we are talking about, for this kind of project, you are looking at a return on investment across 4 months, which is extremely quick. One of the last few slides is on additive manufacturing. So I'm sure that you all heard about it. You know, it's 3D printing, 3D metallic printing, additive layer manufacturing. It's being named in a lot of different ways. So this is the information I can give today. Obviously, it's quite a very key strategic area for us. So I can't give more information than what you have on the slide, but we are working intensively on this. Basically, we started to investigate in this technology around 2 years ago. We are talking mainly around titanium powder and around electron beam melting as well as selective laser melting. The idea for us is not to make a full landing gear in 3D. That's not possible today because of the constraint of the technology. But the idea for us today is more to look at the niche markets on landing gears, the niche products, and try to see how we could employ the metallic 3D printing to produce components with the main goal to save weight. So here is an example of a project you can see. So the original parts, it's an hydraulic part, so you can imagine a lot of internal channels. And the original part was around 12 kilograms. A lot of machining, 50% of the part machined away with a lot of deep hole boring, drilling, and so on. By redesigning the part and producing it in additive manufacturing, using the two different technology, e-beam and selective laser melting, we managed to reduce the weight by over 45%. And we also managed to reduce the number of parts that you can assemble in one component. The big advantage for us as well is that on all those hydraulic components, usually we will have some plugs to to make sure that we don't have any leakage in service. When you produce the part in additive, you design the part you want, so you can create some very organic hydraulic channels, which means that you don't need to put plugs anymore. So you remove all your risk of leakage in service, which is major for us. And I believe personally that this kind of technology will really explode within the next 5 years. Once we start to see the first few aerospace parts being certified, it will find its niche, but we'll see a mass adoption of this technology. So that's for the manufacturing. Before concluding on the presentation, quite a busy but interesting slides on Industry 4.0. I'm not going to give a talk on Industry 4.0. The guy before me was talking about it exactly. So that's more to show that we are looking at it as well. For us, it's extremely important. We want to be leading, in fact, Industry 4.0. We want to have a smart, connected shop floor. We want to be able to know exactly at any given point where each part is on each machine. We want to have the flexibility to move one part from one machine to another. We want to be able to track all the parts on the shop floor, so get rid of your paper, go to paperless, and we want to ultimately have a more efficient shop floor. So the road to get to this point is quite long, especially if you remember I told you that the site was built in 1931. So when you try to introduce new technology, there is a lot of change that need to take place. But we are trying to embrace Industry 4.0 by launching some key projects. And I believe personally that this Industry 4.0 will really take off when you will have your foundation of key enabler projects from which you will build your roadmap and your development. So to conclude, the key enabler to us, it's important for us to continue innovation. Without innovation, we are going to lose our rank of #1 in terms of landing gear system. So for this, we need to continue to work with the supply chain. The supply chain is extremely important in bringing the technology that we can then adapt and adopt for our landing gear. We are always looking at UK and European funding opportunity. When you have funding, you have collaboration, and through collaboration, you can innovate. We won't innovate if we are on our own. As you understood, we work a lot with the Catapult Center in UK, so it's part of our network of suppliers. And also, the academia and the UK government, through the funding of the Catapult Center, is really key for enabling the innovation and making Messier-Bugatti-Dowty a more innovative technology. So that's it for my presentation. Thank you for your time today. And now I can take some questions if you got some. Yeah.
Hello, Bob Griffiths, consultant in Composites.
Okay.
The main vertical member of the undercarriage,
yeah.
You're looking at corrosion problems by going to stainless steel. Why don't you go straight to composites?
So we've tried composites. In fact, if you go on the stand, we've got one of the big landing gear for the 787. We were the first landing gear designer in the world to design side braces for the in composites and to have them certified by FAA. Today, composites, we went through a lot of pain to develop composite for this kind of parts, and we realized that for this kind of part, it's break-even with the current material that we use. So we can talk about steel or we can talk about titanium. So on this kind of part, it's break-even. We had too much difficulty to find a robust production way to introduce them for the mass market. In terms of the largest parts, as you said, it's a steel component, the big main fitting that you can see outside. The reason why it's not titanium is purely because we can't make it in titanium today. We don't have any press in the world big enough. But we have a big project in Gloucester looking at reducing the weight of the landing gear, and I believe that composite is being looked as a potential replacement for this type of part.